Welcome to Module 9. We will begin looking at the thermodynamics property network in this set of videos. Now, our goals in this particular unit will be to find mathematical relationships for the state variables, so pressure, temperature, volume, entropy, and then all of those energies, enthalpy, internal energy, Helmholtz energy, and Gibbs energy. Now, we'll be doing this specifically for pure single-phase substances. When two state variables are known, we should be able to define the third. Then we're going to be using these mathematical relationships to relate theoretical definitions to measurable quantities. Now, this is a mathematically very heavy subject, but it's very useful because if you can do this, you can solve many problems with very limited physical data. Now, to get started on this, let's talk about the Gibbs phase rule. Gibbs phase rule says that the degrees of freedom, which is how many state variables must be defined for a problem to be solved, is 2 plus the number of components minus the number of phases plus the number of reactions. Now, if we have a pure substance, C, the number of components will be 1, and it's not normal for one single substance to react, so R is typically 0, and so in that case you end up with the degrees of freedom is 3 minus pi, the number of phases. Okay, so in a single phase system, pi is 1, so degrees of freedom is 2, and we must define two state variables. As you increase the number of phases, degrees of freedom goes down, and there's less and less to specify. So in this lesson, we're going to be looking at what happens for that single-phase system. In the next module, we'll be looking at two-phase systems. So again, those state variables, we've got pressure, temperature, volume, entropy, enthalpy, internal energy, Helmholtz energy, and Gibbs energy. Some of these we're very familiar with because of our previous thermodynamics work, and then some of these, Helmholtz energy and Gibbs energy, are perhaps very new to you. But the other key thing is 3 of these variables are things that I can measure. So pressure, I can measure. Volume, I can measure. Temperature, I can measure. The rest of these, I really can't measure those. And so how are we able to determine the values that should be for these variables? So let's look first at the fundamental relations. So we've already made some of these definitions. H is enthalpy, is the internal energy plus PV. We also have definitions for Helmholtz energy and Gibbs energy. Helmholtz energy A is U minus Ts, and Gibbs energy G is H minus Ts. Now these are other kinds of energy. We really haven't seen much of an application for them at this point in time. And these are simply true by definition. So it's various combinations of the various forms of energy with pressure, volume, temperature, and entropy. Fundamental relations are the differentials of each of these H or energy terms. So for instance, du is TdS minus PdV, and that was probably derived for you in a previous thermodynamics course. dH is du plus PdV plus VdP, just simply taking U plus PV, I take differential of U plus the differential of the product PV using the product rule gives me this. But from the first and second law, I know that du is TdS minus PdV. Minus PdV cancels, so I end up with the TdS and the VdP that are left. And so I have dH is TdS plus VdP. Now I can do the others because now I have du and dH. I can use du here, again using the product rule here, I can take care of this differential. And I end up with minus PdV minus S dt. That should have a d right there. dg is going to be dH minus the product of TS, the differential over the product of TS. And so the product rule gives me minus TDS minus SDT, and some of these cancel by using the definition of dH from here, and we end up with this. So what we end up with is little forms of differentials that relate to other differentials to the energy differential. We say that those are the natural variables of the energy function. So for instance, in U is has natural variables of S and V. DH is TDS plus VDP, so its natural two variables are S and P. A corresponds to V and T, and G corresponds to P and T. Now, one of the things that you'll notice, although U and H are the energy functions that we are more comfortable with, they're natural variables, the ones where their fundamental relation relates to two specific variables that are changing at the same time. They have that entropy in there. I am not real comfortable with entropy because I can't measure it, and I only have kind of a fuzzy understanding of entropy. But A and G are new energy functions, have variables that I can measure. So that in fact is going to make them quite useful. Now, the next thing I want to talk about is something called Maxwell Relations. And these are partial derivatives that derive from fundamental relations. They are going to be fractions. Sorry about that. It's partial derivatives. Now, if we consider du equals TDS minus PdV, this is saying that the derivative of u with respect to s, if I hold v constant, right, that's what a partial derivative is. If s and v are the two variables, then the derivative of u with respect to s is going to equal t, and because I have so many choices of variables, we choose in thermodynamics to write as a subscript what variable is being held constant. So how u changes with the s is equal to t if I use a constant volume path. Similarly, if I choose to see how u changes with v on a constant entropy path, then this is going to be 0 and I'm left with negative p. So du dv at constant entropy is negative p. Now these are the first derivatives of our energy functions. I could also take a second derivative. The second derivative is going to, well, I have a choice of the second derivative with respect to s twice, the second derivative with respect to v twice, or the second mixed partials. So the second mixed partials are the ones that give us some interesting facts. Because what I can do is, if I take the derivative first with respect to the variable x, and then with respect to the variable y, or reverse the order, first with y, then with x, I can either get the same answer or I can get different answers. From math, we've learned in Calculus 3 that when I do these for continuous functions, taking the second derivative in either order should get me the same answer. Because nature seems to be continuous, then we can apply this definition for continuity and say that whether we take the derivative first with respect to s or first with respect to v, they should be equal to each other. So this gets us this relationship here, that I can take it first with respect to v, then s, or first with respect to s and then v. So instead of writing it as this second order derivative, we could write that as the derivative of the derivative. So here we have the derivative of u with respect to v, and then the derivative of this with respect to s. And this should be equal to, by continuity, du ds, and then take the derivative with respect to v of that answer. Now we found that the answer here is equal to negative p. The answer here is equal to t. So therefore, negative dp ds at constant volume is equal to dt dV at constant entropy. So I've taken one derivative holding V constant, one holding S constant. You see that. Okay. Now this is what's called a Maxwell relation. And so if I look at this right here, it came from S and V. It came from the function that had S and V as the natural variables, U. And these are the second order mixed partial derivatives. So now you need to make yourself do this, okay? So just select one of the other fundamental relations. So maybe you want to choose H or any of them. And you develop your own Maxwell relation. So the steps you're going to take, choose the fundamental relation, write the first order partial derivatives of the function in terms of that energy function's natural variables. Use the fundamental relation to find out what those are equal to, and now take the second order mixed partial derivatives of each one of those. You can use your definitions to do some simplification. Take a moment, do that, pause the video, and restart it to see if you're correct. Alright, so these are the Maxwell relations. The first one of these, dP ds at constant volume equals dt dV at constant entropy, is the one that's determined using the U function. If you chose to look at H, you found dt dP at constant entropy equals dV ds at constant pressure. dP dt at constant volume equals ds dV at constant temperature is another, and negative ds dP at constant temperature is dV dt at constant pressure. Now, can you, if you just look at this set of written Maxwell relations, identify which energy function was used to generate them? It's really very easy. You look at the denominators. Here, this is V and T as the natural variables, so it came from the Helmholtz energy function. This one has P and T as the variables. It comes from the Gibbs energy. So we're going to stop the video here. Make sure that you have these fundamental relations and the Maxwell relations down before continuing. We're going to move on next to seeing how these can be used to evaluate some actually very practical quantities.